Bam, Mr. True. Okay, let's get part 2 done of this related rates video for calculus. A race car is traveling 150 miles an hour and you're 45 feet from the track. So here's the track in blue and you're over here at this orange asterisk and you're with a radar gun. When that car is 100 feet down the track, what speed will you record if the car is actually, again, going 150? Well, it's not coming directly at you, it's sort of at an angle. So you're going to record a slower speed than the car is actually traveling. And the closer that car gets and the more off angle you are, the slower the speed is that you will record. So when we have this scenario, how fast will the speed record on the radar gun? Well, so we need a formula that relates all the variables together, and with the diagram drawn, clearly we have a right triangle. So we can set up Pythagorean Theorem, which is how we're going to start the problem. We can also set up the distance formula and just mark this, say, at, I don't know, 0, 0, and your value 100, negative 45. The Pythagorean Theorem and the distance formula are extremely closely related. You can actually derive one from the other. So we're going to take a look at the Pythagorean Theorem because we see a right triangle. So we have a squared plus 45 squared is equal to the hypotenuse squared of c. All right. So great. We're interested in the rate of change. What speed, miles per hour, are you going to record? So that's the rate of change. We need to find the derivative with respect to time of both sides of this equation. So we're going to have, with the chain rule, and remember it again, we're doing the derivative with respect to t, not a or c, so neither one of these variables are just going to cancel out. We're going to have to do the chain rule for both sides of this. So we have 2 times a, and then dA dt. This is going to be, the dA dt, as I've marked down here in blue, this is the speed, here's side A, this is the speed that the car is actually traveling, and we're told that it's going 150 miles per hour. Now, that's not a problem, but I can't use that value because it's in miles and it's per hour. Now, I could keep the time period, but we're only 45 feet off the track, but we're 45 feet off the track, not a certain number of miles away. So we need to make all these units of measure match. So I've taken 150 miles per hour, I've multiplied it by 5280 to get it into feet per hour, and that's quite a large number, and so I went ahead and divided it by 3600 because there's 60 minutes in an hour and then 60 seconds in a minute, and to convert that into feet per second. So we're going to use 220 feet per second for dA over dt. Plus, well, no, plus nothing, because 45 squared is a constant, so that the derivative of a constant is equal to 0, equals to c dc dt. Now, we are shooting our radar from this orange asterisk to where the car is. So the rate of change that we're going to record is along the hypotenuse. So dc over dt is actually what we're looking for in this problem. So we have 2a, so that's going to be 2 times a. This is length a, the car is 100 feet down the track. So 2 times 100 times dA over dt, which is going to be 220 feet per second, equals to, now what's c? Here's where we actually put the numbers into the triangle and get like a fixed triangle and ignore the whole rates of change for a second. I have to know, if you're 45 feet off the track and the car is 100 feet down the track, the formula is asking for us to know what c is, to know how far away the car is from where we're standing. So when it's 100 feet down the track, c is going to be, well, it's Pythagorean Theorem, so square root of 100 squared plus 45 squared. And then dc, again, over dt. We're going to divide both sides by 2 times the square root of 100 squared plus 45 squared and get dc over dt is equal to 200 times 220, went ahead and do the 2 times 100 there, divided by 2 times the square root of 100 squared plus 45 squared, and we have dc over dt. That comes out to be, off the top of my head, or my paper, that comes out to be 200.6 2 feet per second. Well, that's great, but that's not what the radar gun is going to read. The radar gun is going to read in miles per hour. So we're going to take this 200.26 and we're going to have to, 0.62. We're going to have to multiply that. Let's see, what did we do? We divided by 3600, so we're going to have to multiply that by 3600. We multiplied by 5280. I'm doing the reverse conversion from miles per hour to feet per second. Now we got to go from feet per second back to miles per hour. So we're going to divide by 5280 and get a final speed that we're going to read using the radar gun, which is slower than it actually should be, or actually is, excuse me, of 136.8 or 79 miles per hour. And now at this point, this isn't necessarily a question that you can easily check your work. Like, I can't just take this and plug it back into some kind of equation like you would have in algebra to make sure that the answer you got was correct, but is it reasonable? Again, we were off at an angle, 100 feet and 45. I mean, that's some pretty big angles here, so you should be measuring a speed that's, pretty significantly slower than the actual speed because of the angle in which you're trying to hit the speed of the car. So, if you're thinking about driving your car and people getting tickets for speeding on the drive on the interstates, those police officers are, very, very far down the road. And therefore have a very small angle that they're off from your actual direction now. So that type of scenario, you'll get a more accurate reading. The farther down the road the car is, the smaller this angle, the smaller that you're off of the actual trajectory. So we have, again, a speed of 136.8 miles per hour. And now let's get to that question that I pointed out where you had those panning shots. I'll put them in this video as well, where you're trying to pan with a camera and keep that car in your field of view. So same setup, but now we're going to be looking for the rate. We're going to put a theta in here and find the rate of rotation when the car is 100 feet down the track. Woo! Loving this stuff. For our next example, using the same scenario, we have, same thing, 100 miles and 150 miles an hour, 100 feet down the track. If you are photographing the car, what is the rate of change for theta? I've put that in our diagram here. When the car is, again, 100 feet down the track. In photography, this is called panning, where you're trying to, photograph a moving object and keep it within the frame. So that, a lot of times you get the object is clear, which you're taking a photograph of, but the background is blurred because you're panning. Okay, well, I need a formula, I need some kind of equation that will relate rotation to the sides of the triangle. Well, you've been doing that since you learned trigonometry, or even, geometry in Algebra 2, where you first started learning your right triangle trigonometry, or as we like to say, SOHCAHTOA! Sine's opposite over hypotenuse, cosine's adjacent over hypotenuse, and tangent, which is what we're going to use, is opposite over adjacent. So the tangent of theta is equal to A over 45. And just to clarify the implicit derivation process we're about to go through, I'm going to write this A over 45 so it doesn't look like a quotient. Hopefully by now you're comfortable with this. But just to make sure, this is 1 over 45 times A. So we're going to take the derivative of both sides. The derivative of tangent is secant squared. So secant squared theta. Now it's not just secant squared theta because we're not taking the derivative, we're taking the derivative with respect to time, or t. So we have to do the chain rule, for all of this. So it's going to be secant squared theta times the derivative of theta with respect to the time, or with respect to time. And now we've got 1 over 45a, so we're going to bring that exponent of 1 down, bring it down. Of course, still going to have 1 over 45. And again, chain rule, so it's not just 1 over 45 like it would be if we were finding the derivative with respect to a, but 1 over 45 dA over dt. Okay, well, dA over dt is equal to our 220 feet per second. So we're going to take this out and plug in our 220. And we're looking for d theta over dt, how fast you're having to rotate, angle velocity. So I want to get the secant squared over to the other side of the equation. Well, secant squared is 1 over cosine squared. So if I want to undo a division of cosine squared, I want to multiply by cosine squared. So we're going to multiply both sides of the equation by by cosine squared. And there's only two terms here, one on the left, one on the right. So we're going to cancel this over here. The secant squared is going to cancel out, and when we distribute, and then of course we're going to distribute it to the other side as well. So we're going to have d theta over dt is equal to 220 over 45 times cosine squared theta. Well, don't we kind of have a problem? I don't know what theta is. Now, we can do inverse tangent to find out what theta is and actually figure that out. I've had my notes written in the form of where we're not going to actually find theta, we're just going to use the ratio of what we got going on here. So cosine squared theta, cosine is adjacent over hypotenuse, or excuse me, adjacent over hypotenuse. I'm putting the wrong thing here. So we have adjacent, which is 45. So let's take this out. Remember, it was cosine squared theta. So we're going to put a big square here for that cosine squared part. Now the cosine of theta, again, is adjacent. Here's theta adjacent, which is 45 over hypotenuse. Okay, hypotenuse. So that hypotenuse is the square root of 100 squared, 100 feet down the track, plus 45 squared. And this comes out to be d theta over dt is going to be, again, off the top of my head, oh, let's see here. How about 0.8, well, it's going to be 396. I got an exact form. 396 over 481, or it's going to be 0.823 radians. Now, I put that into feet per second, so it's going to be radians per second. Now, the next example, the third and last example, is going to be a bit of a long one, but I really, really dig it because I'm kind of a car nut. All right, so one more example and we're done. Hey! Last example. Combustion engines, car engines, or tractor engines, or whatever. Internal combustion engines will have a piston inside of it which will move up and down, compressing air, gets ignited by air and a mixture of air and fuel, gets ignited by a spark, pushes that piston down, turns a crankcase, piston comes up, pushes the old air out, down, up, new explosion, and so on and so on and so on. So inside of a combustion engine, you have this relationship of rotational energy or rotational speed and linear speed, or linear in this energy here. So as this piston gets driven up and down, we have linear velocity and linear forces. That gets converted into rotational forces, which then gets sent to your front and rear wheels to power your car or whatever else you might be talking about. So we've got this problem that says that we have a connecting rod, that's this piece right here, that's 2 times the square root of 7 inches. That's me trying to make up a problem I can do relatively easy in my head. A radius for the crankcase, or the crank, which is equal to 2 inches, and this engine is rotating at 600 revolutions per minute. We want to find the speed, the linear speed of this piston when theta is specifically equal to 5 pi over 3. Now I need to give you the actual position of the crank, or we're going to use this diagram here in a second. And the angle is important because, of course, as you have this rotational movement, that's a circular function, that's sine and cosine. If you were to track the path of this piston over time, that would be either a sine or cosine graph, depending on how you want to start the initial position. So this piston is going to accelerate up and then reach its top dead center, in which case at that point, whatever that angle may be, the 90 degrees or pi over 2, the way this is drawn, that piston would top out, and its vertical speed, or the linear speed, would be 0 until it started to fall. And so this piston is going to be, stop, force down, and accelerate down until it reaches the bottom, and then stop again before it starts to move back up again. So it's in constant acceleration and deceleration of motion. So we need a specific angle to find the linear speed. Okay, so that's what's going on. We have this oblique triangle, and there's two laws that we know for working with non-right triangles or oblique triangles when we're trying to find missing sides and angles. And that's either law of sine or law of cosine. Now, the only angle that I care about is theta. I only care about one angle within this, this triangle of connecting rod and crankcase. So I don't want to do law of sine, because law of sine, to do law of sine, you have to know a side and an opposing angle. Well, I know a side and I'm working with an opposing angle. And then we have the two, but I don't know what this angle is. So I really don't even have enough information to really do law of sine. Actually, I do. I could I could put the 5 pi over 3 here. But I don't want to do law of sine because it's going to work with two angles within the triangle. And what I really care about as well is, I have this side and this angle, this side and that angle. And law of sine wouldn't even really be dealing with without a little bit of extra finagling about this side x. So we're going to work with law of cosine. And law of cosine says that a side is equal to what? The other two sides squared and added together minus 2 times those same sides times the cosine of the included angle, or the angle that's opposite the side that you have the equation set equal to. So law of cosine with this is going to say that the 2 square root of 7 squared is equal to 2 squared plus x squared minus 2 times 2 x times the cosine of theta. So we have a function that puts together all the variables of interest for the problem, x and theta. X is going to become the actual linear speed of the piston, and theta is going to be the 5 pi over 3 radians of rotation we have with the problem. So now we need to simplify this a little bit and find the derivative of both sides implicitly, so we can bring motion into the problem. So 2 squared is 4, and the square root of 7 squared is 7. So 4 times 7 is 28 equals 2 squared, which is 4, plus x squared minus 4x times the cosine of theta. We're going to take the derivative of both sides implicitly. So that's going to be the derivative of constant is equal to 0. The derivative of constant is equal to 0. The derivative of x squared, again with respect to time, is going to be 2x times the derivative of x over, dx over dt, the derivative of x with respect to time. Minus, okay, now, I'm putting parentheses in here because this, if I just look at the 4, whoops, not the 4, that's just going to complicate things a little bit. Let's take that 4 out. So we're going to do minus 4. There we go. Now this part, x cosine theta, that's two items being multiplied together, so we need to use the product rule. So we have x times the derivative of cosine, which is negative sine, so I'm going to put a negative here, negative sine theta, and then it's a chain rule because, again, we're doing the derivative with respect to time, so negative sine from the derivative of cosine, and then d theta dt. So that's the first term times the derivative, or the factor, the first factor times the derivative of the second factor, plus the derivative of the first factor, which is going to be dx dt, times the second function, which is going to be cosine theta. Okay, now I'm trying to solve this, of course, for what are we looking for? We're looking for the linear speed. So we're going to be, I don't have it written down anywhere, do I? Okay, that's pretty sloppy. Not like me. So I'm trying to find dx dt, because this is the movement of the piston. So I need to get that alone. I'm going to do a couple of things. I'm going to divide the entire equation by 2 and reduce these to 1 and 2 just to keep my numbers smaller. So we have theta is, or excuse me, 0. 0 is equal to x dx dt. We're going to take the negative 2 and multiply it through the parentheses. So we have negative 2 times negative 2 is positive 2x sine theta d theta dt. And then negative 2 times, so minus positive, so negative 2 dx dt cosine theta. Okay, I'm looking for dx dt ultimately, so I want to get that alone. So I'm going to bring the 2x sine theta d theta dt over to the other side. So negative 2x sine theta d theta dt is equal to x times dx dt minus 2 dx dt cosine theta. I'm going to factor dx over dt out of both of these terms, and that's going to give me negative 2x sine theta d theta dt, which is going to be equal to x minus 2 cosine theta dx dt. Dividing both sides by x minus 2 cosine theta, we get negative 2x sine theta d theta dt all over x minus 2 cosine theta, which is equal to dx dt. Now, what do we got here? We have theta. That is given to us as 5 pi over 3. What we don't have is d theta over dt, and we don't know what x is equal to. So let me go ahead and clear off some board space, and I'm going to take this equation, put it up here, and then discuss with you how we're going to find d theta over dt, because we don't actually know that yet. That is not 600 RPM or revolutions per minute, and we also don't know what x is. So let me get some room to finish this example. I'll be right back. Got our board cleaned up. dx dt equals blah blah blah. Okay, what is d theta over dt? Well, d theta over dt, a lot of students in pre-calculus and trigonometry like to think that when you're given revolutions per minute, you're given angle velocity. But angle velocity is number of degrees or number of radians over time, not revolutions. So d theta over dt is going to be 600 revolutions a minute times 2 pi, and we get 600 times 2, which is 1200 pi radians per minute. Almost put seconds there. Okay, the formula is also asking us for, let's go ahead and put that, well, I'm not going to room anyway. Let's go ahead and put in or figure out what x is now. Well, again, law of cosine. So we're going to, again with some scratch work, I'll need to maybe erase this in a second, but we have, back to that original law of cosine that we set up, 2 square root of 7 squared equals the other two sides squared and added together, so 2 squared plus x squared, minus 2 times the other two sides, so minus 2 times 2 times x. Only this time, unlike what we wrote before, we're going to put in the actual angle measure of 5 pi over 3, so times the cosine of 5 pi over 3. Well, this is going to be, again, 4 times 7 is 28, equals 4x squared minus 4x, and the cosine of 5 pi over 3. Now, pi over 3, remember pi over 3 is 60 degrees. So here's 0, we have 1 pi over 3, 2 pi over 3, 3 pi over 3, I'm counting off 60 degrees, 4 pi over 3, and then finally 5 pi over 3. So on the unit circle, the cosine of 5 pi over 3 is equal to 1/2. Well, 1/2 of 4 is equal to 2. So we have, let's just clean this all up at once here. We have 0 is equal to, we have x squared. We have negative 4 times divided by 2 is negative 2, so negative 2x. And we're going to bring that 28 over with subtraction, and 4 minus 28 is negative 24. This is a factorable trinomial. If it were not, you'd resort to quadratic. You'd result to using a quadratic formula, but this is just going to be x minus 6 times x plus 4. So we have an x value equal to 6 and negative 4. Now, this length of x, that's how far away the piston is away from the center of the crank shaft, can't be negative. So we're going to have to pick the positive value of 6. Okay, so now we've got d theta over dt, we have theta, we have x. Let's get this done. Negative 2 times 6 times the sine of 5 pi over 3. Right there, 5 pi over 3. We have d theta over dt is equal to 1200 pi. Well, let's talk about pi's making me hungry. X is equal to 6 minus 2 times the cosine, again, of 5 pi over 3. We have, let's see, we have negative 12. We have the sine of 5 pi over 3 is negative square root of 3 over 2. And we have 1200 pi over, that'd be a lot of pi to eat, 6 minus 2 times the cosine of 5 pi over 3 is again 1/2. We've got negative times negative is positive, and we have 12 divided by 2, which is equal to 6. And we have 6 times 1200, so that's going to be 7200 pi. Let's see, can't forget the square root of 3, so how about 7200 square root of 3 pi over half of 2 is 1, and 6 minus 1 is equal to 5. What are we doing here? Inches. Inch per, I don't need an inch and a double line, inches per minute. Now, I don't think anybody without a calculator is going to know what that really means, so let's put that into a calculator, and we get 72 pi, 72, I'm just checking my work here, 7200 square root of 3 pi over 5 is equal to 70, well, roughly, approximately equal to 7835.6 inches per minute. And if you like, you could actually convert that into miles per hour, but I don't like. So, I'm Mr. True. Bye! Go do your homework.